All right, this is your second vectors lesson. In this lesson, as the title says, we're going to be working with vectors. Some of the same ideas that we've worked with in the first lesson. We'll do some applications. As you can see, the objectives, we're going to calculate distance between points. We're going to write unit vectors. The symbol shown here is read as a hat, and this picture here obviously is also a hat. So that's the connection there, quite funny. Find vectors of any magnitude in the direction of a vector and add and subtract vectors, and we're also going to prove geometric relationships with vectors. All right, so let's get started. The distance between 2 points, all right, basically it comes down to Pythagorean theorem. It can be done in 2 dimensions and 3 dimensions, and basically the distance formula is the root of the sum of the squares of the components. Once you've found a vector between 2 points, you just simply take the square root of the sum of each of the components squared. All right. As you can see in here, this is what we talked about last day, defining the vector AB as the position vector of B minus the position vector of A. So we're using that again. So for the first question here, find the vector AB between these 2 points. Very common first question on IB exam. And so the vector AB can be expressed as OB minus OA. Write that, you get a point. All right, pretty much. And put in their position vectors, which is just converting the ordered triples into position vectors. So we have 2, 5, -3, minus OA, -2, 3, 1. And subtracting those, we get 2 minus -2, which is 4. 5 minus 3 is 2. -3 minus 1 is -4. So those are the components of vector AB. Again, what that tells you is that's how you would move to go from A to B. 4 to the right, 2 up, -4, I guess, into the board in the 3rd dimension. All right. Now, to find the magnitude of AB, which is basically what the distance is saying, is the calculation is going to be, again, magnitude AB is equal to the root of, and this is where I'm saying just the sum of the squares, the root of the sum of the squares of the components. Okay? Just like that. And so this is the root of 16 plus 4, 20 plus 16, so 36, which can be simplified to 6. So it's 6 units long. And that's the distance from A to B. Now back to unit vectors. Last day, in Vectors 1, we talked about unit vectors in each of the 3 principal directions, in the X direction, Y direction, Z direction. I is the letter that denotes a move of 1 unit in the X direction, J 1 unit in the Y direction, and K 1 unit in the Z direction. Today we're talking about unit vectors, but we're talking about a unit vector in the direction of a given vector. All right, so that's why it has the name A. A will be the name of our vector. Obviously it can be any other letter as well. But what we'll want to do is we want to find the vector that is 1 unit long in that direction, and that's what the definition of unit vector is. All right, so for example, vector A here, the first thing you have to do, by the formula, I'll just go back to the formula here, the formula for unit vector, it's not in your formula booklet, that's important to know, but anyway, it's the vector divided by its magnitude. All right, so the first thing you have to do here is find the magnitude of A. Anytime you want to find a unit vector, you have to find its magnitude, so it's going to be the root of 5 squared plus -2 squared, which is the root of root of 29, like that. And now the unit vector is simply going to be, actually one thing I'm just going to change, or also just add in addition here, is that the formula here can also be expressed as 1 over the magnitude of vector A times vector A, like this, okay, as a product. And that's how I'm going to write this one. I'm going to write it as 1 over root 29, 5i minus 2j. And as you'll recall, when I did this in class, I said you can also distribute the 1 over root 29 onto the different components. Okay, so this could be 5 over root 29I minus 2 over root 29J. And just so you understand, all these forms are interchangeable. You can either do it in component form, distribute or not distribute. You can also do this in column vector form. So this could be 1 over root 29, 5, negative 2 like that. Or you can also distribute in column vector form. And that would be 5 over root 29, negative 2 over root 29. So all these four forms are acceptable, and they're interchangeable. And you can represent your unit vector in any of these forms. And then last here we'll do question B here. Again, it's no more difficult. It's just a vector in 3 dimensions. Again, the first thing we want to write its unit vector is you need to find the magnitude of B, and so that will just be the root of, again, negative 3 squared plus 6 squared plus 4 squared, which is equal to root 61. Okay, and again, B hat is going to be, in this case, 1 over root 61, and then all the components of the vector, negative 3, 6, 4. All right. Just a couple notes again. Remember, under the radical, everything should be added. Put negative terms in parentheses. Make sure when you square, you get a positive quantity, and everything is added. You'll never get a negative under the radical. Okay? Make sure everything is added. Just one thing I just wanted to show here too, and I showed this in class when we talked about it, but if you want to find unit vector, the whole idea behind unit vector is basically based on similar triangles. So for example, if we use this triangle again, our 3, 4, 5 triangle that we've been working with, if I want to reduce it down to a length of 1, okay, so for example, if I want it to now be 1 unit long, let's say it's right there, okay, what I've done to make this 1 unit long is I've scaled it down by a factor of 5, all right, so its original length was 5, but to get it down to 1, I had to divide by its length, and I also have to do that with each of the components, so that horizontal component becomes 3/5, and this vertical component would become 4/5. And so this vector as a unit vector would be 3/5 I plus 4/5 J. Okay, and that's what makes it a unit vector. It's 1 unit long, and the sum of the squares of the components will add up to 1. All right, you can test that what I just said by even, for example, in here. If you want to test and see if you've actually found the unit vector, this unit vector needs to be 1 unit long. So if you square 5 over root 29, you should get 25 over 29. And if you square negative 2 over root 29, you should get 4 over 29. If you add those two together, you'll get 29 over 29, which is 1. Okay, and again, that's what we want out of this, is we want a vector of length 1. Okay, and that's what a unit vector is. But again, if you're having trouble thinking of the formula, just think about scaling it down by a factor of its magnitude. Okay? All right. And now the way we'd use unit vectors is if we want to create a vector of a certain length. So if you want to make something be a certain length, a certain number of units long, the easiest way to do that is to reduce it down to 1 unit long, and then multiply it by whatever length you need it to be. So, for example, in the last case, if we were using that vector that was the 3, 4, 5, so it's 5 long, but if we wanted to make it 11 units long, for example, the easiest way to do that would be to reduce it down to a unit vector and then multiply that unit vector by 11, and it would be then 11 units long. And basically, again, that's what this formula is saying. So we have our unit vector A over magnitude A times K. And again, it's important to know that K could be an element of the reals, any real number. Positive, negative, okay? Fraction, decimal, rational, irrational, doesn't matter. All right? So now to find a vector that's 10 units long in the direction of this vector, 2i minus 3j plus k. Again, easiest if we can just name it. So I'll just call this vector A. A is equal to that. So the first thing I'll do is I'll find the magnitude of A, which is the root of just the squares of the components again. 2 squared plus negative 3 squared plus 1 squared. which adds up to 14, okay? And the unit vector A is equal to, again, 1 over root 14, and then either in its component form or column vector form, 2, negative 3, 1. Then I'll just write it here, 1 over root 14, 2i minus 3j plus k. Those are equivalent. And then if we want a vector that's 10 times that long, what we want to find is we want to find vector 10 times a hat. And that will just look like this. We multiply the vector a hat by 10. So in this case, it could look like this. 10 over root 14, 2i minus 3j plus k. Or you can again distribute this out, and this would be 20 over root 14i minus 30 over root 14j plus 10 over root 14k. And again, interesting to note, if you tried to find the magnitude of this final vector here, you would square each of the components. You get 400 over 14, 900 over 14, 100 over 14. You add 400, 900, 100, you get 1400. 1400 divided 14 would be 100. The root of 100, which is what you're going to do, you're going to take the square root of the whole thing, gives you 10. So you've made a vector that's 10 units long, which is the purpose of finding the unit vector and then multiplying by a chosen scalar quantity, a chosen magnitude. All right. Moving on here. Adding vectors. The big thing with vector addition graphically is that you need to add them tip to tail. That's the key. All right, but I've not seen many IB questions come where you've had to add vectors, actually graphically add them, but it's important to understand how they are added. And again, all this means is, for example, if I had vector u here, which is 5 units long, and it's moving straight in the positive x direction, let's say, that's 5 units long. If I had that vector, and then I wanted to add vector v to it, I'd lay down vector u, like it's shown here, and then put the tail of vector v at the tip of vector u, like this, all right? And then the resultant is the vector from the tail of u to the tip of v, as shown in yellow, all right? So that's the important thing to know about vector addition graphically. You have to add them tip to tail. Adding vectors algebraically again, here's another question A. I'll just go over it really quick. It's AB plus BC plus DE plus CD. All right. Again, we can put two vectors together if they pass through the same letter. So it makes sense here to add AB and BC, and that's going to give us AC. And the other thing to know about vector addition is that it's commutative, and that means the order doesn't matter when you add. So I can shuffle or shift vector CD and DE. So it can be like this, CD plus DE. And at this point, I can choose to group any two of them. I can do AC and CD together, which will give me vector AD plus DE. And now I can choose to add, I can obviously add AD plus DE, and that will give us the final answer of vector AE. All right, as long as you pass through the same letter, basically you're eliminating that common letter. I won't go through B, it's long, it takes a little bit of time, and we don't want to spend the video doing that. So I'll give you the answer though to it. The answer that I have for it is 2BD. So try it yourself. It's a good little exercise to go through. Subtracting vectors. It's an interesting thing about subtracting vectors because there really is no vector subtraction as such. The way you subtract vectors is by adding the negative of the vector. All right, so it's really just addition of vectors, but you're adding the negative. Again, if you want a pictorial case of this, kind of using the vectors that we had in the previous question, if I had u like this, and I knew that vector v, let's say, looked like this, and I wanted to do u minus v, oh, that's what's actually being shown in the red here. I'll just overline it. Okay, U is here, horizontal, and now if I want to subtract V, I'm actually going to add the negative of V. And the negative of V, what's important to note here is that the negative of V is the same length, but just the opposite direction. And so this is negative V here, all right? And then the resultant is the vector across from the tail of the first vector to the tip of the second, all right? We'll just look over some of the, I'll do part C, 5C with you. To do it, all we have to do is, there's some scalar multiplication involved and then a subtraction. So it may look like this. It's going to be 3 times vector B, negative 1, 3, minus 2 times vector A, 2, negative 1. And now you need to distribute the scalar onto each of the vectors. So we're going to multiply 3 times negative 1. We get negative 3. 3 times 3, 9. And now there's a couple ways you can handle the subtraction here. You can keep it as subtract. Maybe I'll do it that way. I'll keep it as subtract and then distribute the number 2 onto these two terms. So 2 times 2, 4. 2 times negative 1, negative 2. And now we can keep it as a subtraction. So it's negative 3 minus 4, which is negative 7. 9 minus negative 2 is 11. All right, so we get the vector negative 7, 11. The only other thing you could have done here differently is you could have distributed negative 2 onto the column vector 2, negative 1, but then the sign in between would have become positive. So if you want, you can do it that way, but just make sure you know and understand what you're doing. Number 6, we'll leave these to you as well. Just note that here in B, P minus Q over 2 is the same as P minus half Q. So all you're doing is you're multiplying the vector Q by a half, the scalar quantity of 1/2. And then the last thing here is the zero vector. There is such thing as a zero vector. You may have noticed it in the algebraic addition of those vectors. If you end up with going from the same point, like A to A, for example, that would be the zero vector. You haven't moved at all. Going from A to A is just zero movement in all directions. All right, and that's really what's represented by the zero vector. And the two cases, two and 3 dimensions are shown here. This last example here is just a way of showing or proving that when you join the midpoints of two sides of a triangle, that the side that you add is parallel to the third side and half of its length. So we could just draw a picture for this. This is what we're saying. Okay, so let's say this is our triangle. We'll label it A, B, C. We're going to put a, again, what we're doing is we're joining the midpoints of the two sides. So we're joining the midpoints of AB and BC. So we'll label those points D and E. And ultimately what we want to figure out is we want to figure out if DE is parallel to AC and if it's half of its length. So the things that we know, the way we've set this question up is that D is the midpoint of AB, so that segment is equal to that segment, and E is the midpoint of CB, so this segment is equal to this segment. All right. So there's a couple of vectors that we can set up to do this. Some of the things that we know then in terms of vectors is that vector DB is actually half of vector AB. All right. We know that vector EB is also half of vector CB. Okay. So the thing that by vector addition now, if I wanted to get the vector AC, the two vectors that I would have to add together to get vector AC would be vector AB, so going from A to B, and then B to C. That's using our graphical vector addition principles. So that equation I could write then as AC is equal to AB plus BC, like that. And I can do the same thing in terms for DE. So DE would be like this. Vector DE is equal to DB plus DB plus BE. Obviously, those are and by the algebraic principles that we've learned, those work as well. And again, going from D to B, and then B to E would result in vector DE. All right. Now we can do some substitutions with the things that we've found already. We've already said that DB is equal to half AB, so I can substitute there. And now I'm looking for an expression for BE. So we're going to just switch the letters around in the vectors that we found over here. So we'll make this vector BE, all right? And that's equal then to 1/2 vector BC. As long as I'm doing the same thing on both sides, it's equal. So this is plus 1/2 vector BC. And again, as long as my component, my scale is the same, I can actually factor out the 1/2. It's the same, so what AB plus BC, and again by vector addition, AB plus BC will equal AC, and that's what we've been trying to prove. So what we're saying here now is that DE is equal to half of AC, so that means it's half the length of AC, and if it's equal at all, and any scalar multiple, it's also parallel. So that proves that it's parallel and actually half the length. All right, and again, we have a long video. Sorry. Enjoy though.